Let's get started. I'm so glad to have you all with us as we dive into a really amazing new set of features that VMware has recently added to its platforms. From my perspective, virtual volumes represents a paradigm shift in the way that we think about storage. My name is Joe Cooper, and I'm an instructor with VMware Education. I'm here with Rawlinson Rivera, a principal architect for storage and availability with the Office of the CTO. Rawlinson will be available to answer our questions at the end of the presentation. Our time is quite compressed this morning, and we've got a lot of exciting stuff to cover. So without further ado, let's begin. At VMware, we've been speaking about and really evangelizing the concept of the software-defined data center for many years now. And while this vision of the SDDC may have begun at VMware, we have certainly seen that these ideas have become embraced by IT teams around the world. Now, what does it really mean? The idea behind the software-defined data center is that we begin to decouple the software that we use to manage our environment and the applications that we run our businesses on from the physical hardware that we run it on. The execution of this vision allows us to become more agile as we respond to changing business conditions, more flexible as we decide how to implement our infrastructure, and certainly more efficient in our use of the physical resources at our disposal. As we abstract our resources from the physical hardware from which they're derived, we pull those resources together and we automate the provisioning of these resources. We create a software-defined data center that is far more easily consumed and delivered than ever before. Now, there are four key pillars of the software-defined data center. First, we expand compute to all applications. Next, we virtualize the network to increase speed and efficiency. And third, we replace manual approaches to IT management with automation. Now, the last pillar is about transforming storage by introducing a new operational model that is driven by the needs of our applications. We know that storage has long been a critical piece of every data center. And while we've recently been witness to a massive expansion in the capabilities of storage subsystems, the way that we manage and provision our storage has been, for the most part, consistent. Some might even say stagnant for many, many years. Now, as time has passed and software has advanced, we look to our storage systems not simply to provide capacity for us, but to really facilitate this data-driven era that we've now entered. Now, while capacity and speed are important, and in fact they're critical to our daily lives, we've come to expect more out of the storage systems that we're placing in our data centers. The industry is changing, and new competition and new technologies are changing the way that we think about IT and what it can deliver to our lives. But as we think about these changes, it's especially important to understand the challenges that are being seen in today's data center. The fact of the matter is that our traditional storage architectures can't keep up. Beyond that, the systems that we're placing in our data centers aren't cheap. I think that most of us would agree that the storage infrastructure is the single most expensive capital investment that we make in our data centers. We don't screw around when making these purchasing decisions. We don't buy commodity hardware. Nobody ever got fired by buying all the good stuff. But as we implement, we find that our storage systems are underutilized and they're over-provisioned. Processes from the storage administrator begin by creating tiers of storage on our shiny new hardware. We provision capacity and performance levels. We implement cool features like compression and encryption, deduplication, replication, and on without ever thinking about what our applications themselves actually need. Then as we determine that applications aren't getting the performance or the features that they actually do need, we have to migrate. And this process is complex, it's time-consuming, and it's fraught with peril. We've got this vicious cycle that involves storage administrators who are responsible for running these systems, application administrators who are responsible for making sure that these applications get what they need from the storage systems, vSphere administrators who are responsible for making sure that application admins and storage admins don't kill each other. I find typically that copious amounts of single malt scotch usually do the trick. But the problem is that if we actually do want to remain sane and even a little bit sober through the process, we've got to come up with a better way. VMware and its partners in storage think we found that way. We hear this question all the time: why is VMware entering the storage market? The answer is simple. With the hypervisor, we have a unique opportunity to change the way that we address the storage challenge. The hypervisor is uniquely positioned in the IT stack to have visibility to see what applications are running in VMs at any given time, and has a global view of the underlying infrastructure. And because the hypervisor sits directly in the I/O path, it has the unique ability to make optimal decisions around matching the demands of virtualized applications with the supply of and the capabilities of the underlying physical infrastructure. The result is that the hypervisor enables a new approach to storage that puts applications in charge of defining their own storage requirements. Virtualization is the gateway to enabling a new way of provisioning and managing storage that lets software manage storage needs. So let's see how all this works. Let's start by looking at how we provision storage today in a model where it's the physical infrastructure that dictates how we utilize storage. We begin by building LUNs, right? The LUN is our focus. Within our arrays, we build a LUN to the specification that determines its capacity, its performance, and its features. And anytime we want to work within that environment, we work with that LUN. If we want to enable compression, we compress the LUN. If we want to deduplicate or replicate, we dedupe or replicate that LUN. If we need more capacity or performance out of our storage, we achieve that by managing our LUNs. All of this is done with tools that are provided by our storage vendors. Of course, if you want to work within an environment that includes storage systems from multiple vendors, you have to use multiple tools to manage those systems. So fine, we've been doing it that way for many years. We can manage. What other choice do we have? The problem, though, with all of this is that not once in that little story of the lonely LUN did we ever mention the word application. The poor little application, the most important thing that we have in our entire data center, has to beg and plead with the LUN so that it can get what it needs from the array. Well, something's not right about this picture. All right, so let's flip it on its head completely here. We're calling for a revolution. It's time for the application to stand up and demand that our arrays deliver what the application needs. Now, I joke, right? But if you really think about it, by driving our storage systems from the perspective of the application, we can go much further to bring the ideal of the software-defined data center into fruition. Now, we can very quickly provision storage resources for applications. We can deliver then just the capacity, just the performance, and the features that our applications need, as opposed to building entire LUNs to those specs. We can automate quality of service so that if we get into a situation where we're running low on resources, where we're under contention on our arrays, we can ensure service levels on our applications. And if we need to make a change in the system, we don't have to break out the good stuff. Oh, and by the way, we can do this all by managing applications regardless of which array they happen to be on and in which management tools the vendor has provided. VMware's foray into software-defined storage began with the release of vSphere 5.5 and Virtual SAN, where we introduced this application-centric model to storage that was internal to your ESXi hosts. With the release of vSphere 6 and Virtual SAN 6, we significantly improved and extended those feature sets by allowing an all-flash architecture. We doubled the scalability of a vSAN cluster from 32 to 64 hosts. We doubled performance on hybrid clusters, and we quadrupled it on all-flash clusters. And we completely changed the way that we execute vSAN snapshots and clones under the new Versto file system. Now, to extend the software-defined storage control plane to existing external storage, VMware introduces virtual volumes. vSphere Virtual Volumes is a management and integration framework that virtualizes SAN and NAS and enables virtual machine-centric operations while leveraging all of the very cool native array-based capabilities that VMware storage partners provide. Virtual Volumes leverages the same management and automation engine of Virtual SAN. We call this storage policy-based management. This enables us to automate the delivery of storage service levels with virtual machine granularity. vSphere Virtual Volumes is an industry-wide initiative that's supported by all of the major storage vendors. This allows us to leverage our current investments in storage while transitioning to this new software-defined, application-centric paradigm. Both Virtual Volumes and storage policy-based management are offered as standard features on the vSphere platform. As we begin to speak about concepts in Virtual Volumes, we need to understand that what we've done here is that we've created a more efficient operational model for our external storage arrays. Some basic concepts here. Virtual Volumes virtualizes SAN and NAS devices into logical pools of capacity we call virtual data stores. In traditional storage models, the array itself has no concept of a virtual machine, no concept of a virtual disk, a VMDK. Arrays know about LUNs, that's it. With Virtual Volumes, the VMDK becomes a native object on the array itself. The array looks at the virtual volume, a VMDK for example, as its unit of management. No longer are operations done on a per LUN level, they're now done on a per virtual volume level. It becomes possible to execute storage operations with virtual machine granularity and to provide native array-based data services to individual VMs. To enable efficient storage operations at scale, Virtual Volumes uses vSphere storage policy-based management. We support existing storage protocols like Fibre Channel, iSCSI, NFS, FCOE. We're based on industry standards, and we have support from all of the major storage vendors. Finally, both Virtual Volumes and storage policy-based management capabilities are included in all of our vSphere license packages. Let's start by outlining what we know about our current storage paradigm. Let's start with our file systems. Today, the entire file system's purpose, among other things, is to act as a volume manager. It helps us to create VMDKs, and it provisions those VMDKs onto a LUN. In vSphere, we know these file systems as data stores. So far, everybody on the same page? All right. I want you to forget about all of that. Forget everything you ever knew about how we put VMDKs on the LUNs and data stores, all right? That whole idea is going away to be replaced with something better, with Virtual Volumes. What you're looking at here on this slide is an overview, a very high-level diagram of the whole Virtual Volumes architecture. Now, we're going to spend some time on each of these different pieces that you see here, because Virtual Volumes introduces some new concepts that you might not yet be familiar with. As our presentation continues, we'll dive a bit deeper, but for now, let's just take a quick walkthrough of a couple of things, right? First, we have the concept of a virtual volume itself. What actually is a virtual volume, right? Next, we're going to have a look at the concept of a virtual data store. From there, we're going to have a look at the protocol endpoint, what it is, what it does, how the hypervisor uses this as a data path to the array. From there, we'll have a look at the new features of Vasa 2.0. This provides the hypervisor some insight into what features and capabilities the array can deliver to our applications, and it's the method that we use to instruct the storage array to handle all of the provisioning operations, right? Then we're going to take that information delivered from Vasa to create storage policies. Those policies will be used for our virtual machines. Throughout this whole life cycle, the storage admin really just cares about a few things: capacity management, access control, data services that we're able to deliver, meeting application SLA requirements, and certainly data security. Now, the vSphere admin, on the other hand, cares about being able to provision storage for virtual machines on demand. making sure that he's able to deliver the application's appropriate virtual machine level data services. And like the storage administrator, the vSphere admin cares about meeting application level SLA requirements, but not just at the time that the VM is built. He's also responsible for maintaining SLA compliance throughout the entire life cycle of the VM. Now finally, with virtual volumes, we're able to live in a paradigm where these two responsibilities can work together seamlessly and without conflict. Of course, any paradigm-shifting platform wouldn't be complete without being able to support all of the great features that we've come to rely on. Storage policy-based management, thin provisioning, linked clones, native snapshots, NFS, iSCSI, fiber channel over Ethernet, the View storage accelerator with content-based read cache, vMotion, storage vMotion, DRS, cross-host storage vMotion, the vSphere software development kit, and all of the vSphere and vCenter APIs. vSphere data protection advanced, thank you. vSphere data protection, View, vRealize operations, vRealize automation, stateless booting and host profiles. All of those features are supported on vSphere virtual volumes. So what the heck is a virtual volume? When we first tell people about virtual volumes, we understand their impression is that a virtual volume is a new type of LUN. That is not the case at all. The LUN doesn't really do anything for us. It doesn't give us granular enough control over our environment. Virtual volumes brings the focus away from the LUN, and in fact, in virtual volumes, the concept of a LUN doesn't even exist. To put it into a perspective that we might understand, Neo, there is no spoon. With virtual volumes, there is no LUN. Virtual volumes focuses on the application and the virtual machine that it's running in. So the virtual volumes are the files that make up our virtual machines. But I have to be careful about using the word files here. We're not really running a file system. Virtual volumes works on an object-based system. So virtual volumes are the objects that make up our virtual machines. Now here's the cool thing about working with objects. Not all objects are created equally. So by separating these objects into separate virtual volumes, we can create rules that determine how we treat each of these objects. I'll give you an example. Say we've got a super mission-critical virtual machine and it's running on a traditional storage array. The VM is then stored on a LUN, and it's built on an array that supports replication, and we want to use replication for this virtual machine. So what do we actually replicate? Do we replicate the VM? No, the array doesn't know from VMs. We have to replicate the entire LUN. Okay, now in virtual volumes, the storage array is fully aware of each of the virtual volumes it's managing, so it can replicate just the virtual machine. It can replicate it to a separate array. It can create multiple replicas, multiple VMDKs on multiple disks internally. But really, why would I even want to replicate the entire virtual machine when I just really need to focus on the mission-critical objects within that VM? What about something like the swap files? In a large VM that has a large memory allocation, I might have large swap files chewing up expensive capacity. An active replication of that swap file might even chew up bandwidth if and when the swap file changes. But why replicate a swap file at all if when I have to fail over to a different storage array, maybe because of a catastrophic failure, and the VM is restarted as the result of an HA event, that swap file is recreated from scratch anyway. I don't need to replicate that swap file. So it's important that we're able to treat our individual virtual machine components individually. In virtual volumes, there are 5 different types of objects. We start with the config object. That's all the metadata objects relative to that virtual machine. It's the VMX files, it's the log files, it's the NVRAM files, all those little files, right? The data objects, those are our virtual disks. Mem objects, those are our native snapshots. We have swap objects, and then we have other. These are other objects that might be specific to a particular VMware solution, like Horizon View, vRealize Automation Center, those sorts of things. What we're going to see in the vSphere web client looks just like our traditional data store and all the files within it. When we look at these objects from the perspective of the array, on the other hand, we'll see these listed by the object type. The array is fully aware of virtual volumes. The next thing we need to understand are the new concepts of storage containers and protocol endpoints. Once again, in order to understand the job of the PEs and the SCs, we need to refer back to our traditional storage. In our traditional storage story, our lives revolve around the LUN. And the LUN does two different things for us. First, the LUN is our unit of storage. The LUN is used as a container to store our virtual machines, our VMDKs. In other words, the LUN is simply a place where we place our files. But that's not all the LUN does for us. The second job of the LUN is to serve as our access point. It provides the data path that the hypervisor uses to execute SCSI commands to and from our arrays. So the LUN does two things. It acts as our access point and it acts as the storage itself. But by trying to do both of these jobs, we've introduced several challenges. First, as you know, there are limits to LUNs. And every time we reach that limit of capacity, for example, we have to create a new LUN with its own access point. So we end up creating smaller LUNs and smaller access points, and then the problems become intertwined. So when VMware engineers sat down a couple of years ago to start the process, they very quickly realized that if they were to separate these two jobs into two different constructs, we gain a vast amount of flexibility in the environment. After all, how many access points do we really need? Well, if you think about it, you'd need one access point for your NFS systems, another for iSCSI, maybe another to access Fiber Channel, but I certainly don't need an access point for every single chunk of storage on my array. So, maybe we only need one access point per storage protocol. And we certainly don't need a huge number of chunks of storage. We simply want a nice storage container that we can work with. We want to be able to expand it, to shrink it. We want to be able to have our way with it, so to speak. We want to be able to scale our storage in multiple dimensions and no longer be bound by the size limit of a LUN, which is now 64 terabytes. And we don't want to be bound by the number of LUNs accessible from a single host, which has been stuck at 256 for ages. Now, by separating these two jobs of a LUN, a couple of really great things happen. First, we're no longer bound by this limit of 256 connections because we really don't ever need 256 connections. Why? Because we no longer need one connection per small chunk of storage. There's no way that we'll ever hit that 256 connection limit. And at the same time, we can keep scaling our storage well beyond that 64 terabyte limit that we have come to know for a LUN. It's actually quite brilliant if you think about it. With just the single change of separating the access point from the storage itself, we kill two birds with one stone. We address the LUN size limit and the limit to the number of connections to a single host. So with that, let's go talk about the storage capacity itself. Now at this point, the story here is still a little bit fuzzy. We've just gotten through telling you that we're completely abandoning the concept of a file system that we've been using for 30 years, and that ESXi is no longer responsible for building VMDKs. It's now the job of the array itself to do that. Wait a minute, what? So my mind is blown a bit here, right? We've turned that whole world upside down. But if you actually think about it, we know that the hypervisor really spent a bunch of time and energy doing that work. It's certainly a big weight off the shoulders of the host, and beyond that, we've removed all kinds of limitations that dictated the way that we worked within our environment. And I, for one, am glad to be out from under the complications introduced on our environment by the imposition of LUN limits. So as a storage administrator, one of my responsibilities is to manage storage capacity. So you might ask yourself then, in a virtual volumes world, how do I do that? Well, what do we do now? Now we live, drink, eat, and breathe LUNs. Now with virtual volumes, all of a sudden, there are no more LUNs. Instead, we have these hundreds of thousands of objects lying on our array. Now, do we expect you to manage each and every individual object? Obviously not. We might have an array vendor that supports hundreds of these objects. We might have an array vendor that supports millions of these objects. We definitely don't want to be spending time managing these individual objects. So this is exactly where managing storage capacity in the virtual volumes world comes into play, with the storage container. So you already know this, right? We already know what the storage container is. We remember that we're separating the two jobs of the LUN. The PE handles the access point, and the storage container handles the capacity. Now, we can't just drop a bunch of virtual volumes willy-nilly on an array. We need some sort of construct to manage logically and group our virtual volumes. That's what the storage container does for us. It does the second half of that LUN's job, which is simply to store the objects that have been created by who? Created by the ESXi host? No. Storage objects are actually created. They're provisioned by the array itself under the direction of the ESXi host. So who exactly creates this container? The storage admin creates it, exactly. So on the storage array, we need to build at least one storage container to group the virtual volumes that we're about to provision on the array. But you might choose to create more than one storage container. The process will be very similar to creating that LUN, but we'll do it without any of the size limitations of the LUN itself. The limit to the size of our storage container is only dictated by the amount of physical storage on our array. Right? We can start our storage container very small and grow it as needed on the fly. We can start very large and shrink as we determine that we might need a bit more granularity. It's all left entirely up to you, and it really gives you the flexibility to be creative in developing the solutions that you need to satisfy the business requirements of our organization and not be limited by some sort of technical barrier. If there's one limit that we have, is that our storage container cannot span multiple arrays. Yet. Your storage container, for now, must exist entirely within a single array. Now, one last question to think about. Once we've got this storage container set up, how do we access it? We access it through the protocol endpoint. That's right. More on PEs in just a little bit. So remember, throughout this entire workflow, the PE and the storage container remain separate. There's no dependency between the two. Capacity is based on physical storage capacity. A single storage container can be simultaneously accessed from multiple protocol endpoints. So what's the difference then between a data store, where we store virtual machine files, and the storage container, where we store virtual machine objects? Not a whole heck of a lot if you think about it. In the past, we created a data store on a LUN or on an NFS export, and we used it as a way to understand where our virtual machines were stored. Now, instead of selecting the LUN where we build our data stores, we'll choose our storage container. If you think about it, we really don't need, at least technically, we don't need a data store. We've got a protocol endpoint to provide the I/O access point, and we've got a storage container as the destination of that I/O. But why then a data store? Why do we still need to create a data store? Because throughout the VMware world, our products know, love, and understand the concept of data stores. So rather than having to re-architect every product that relies on data stores to provision virtual machines, we'll introduce the concept of a virtual data store. So it is managed in a similar fashion within vSphere, but you see that red X on there? There's some additional goodness involved too. So by now we should have a very clear understanding of the differences between the storage container and the LUN. First, we remember that the LUN does two jobs. It's the access point, and it also provides the capacity. Virtual volume separated that out and uses the storage container to simply provide the capacity. In doing so, we've removed all of the LUN's limitations. And like it says on the slide, the size is based on the array's capacity. The maximum number of storage containers really depends on the array. It's going to depend on your individual vendor. Storage containers can be dynamically extended, and they can distinguish heterogeneous capabilities for different VMs provisioned on that storage container. In other words, we can assign separate capabilities to different virtual volumes. On the LUN size, on the other hand, we have a fixed size for the LUN, and there's a maximum size to it as well. So that's going to mandate in a larger environment lots of LUNs. Okay? LUNs need a file system. VMFS is our file system of choice, right? NFS works as well. Now, within a particular LUN, we can only apply one set of capabilities across that entire LUN. We can't, within the LUN, assign different capabilities to different VMDKs, right? It's assigned per LUN. And then everything is managed inbound from ESXi host to the storage array via that LUN with the file system commands. Okay? We do it a little bit differently as we'll learn when we look at the Vasa Provider a little bit later. We do it a little bit differently in an out-of-band management system with virtual volumes. When we look at the workflow, we're always concerned with what we see. What's under my control as the vSphere admin? What's the responsibility of the storage admin? So it's good to become familiar with the tools that each role uses and what they see using those tools as they work with virtual volumes. The first thing that happens is that the storage administrator is going to create that storage container. He'll also create the protocol endpoints. More on that in a few minutes. The vSphere administrator is going to map that storage container to a data store. Now, once again, why are data stores still utilized? Because all of our interfaces expect us to provide a data store location when referring to virtual machines. Okay? From the vSphere storage administrator side, he sees virtual machines. That's the vSphere admin. The storage administrator, he'll see virtual volumes. So on the vSphere side, we create data stores in the same way we always have, except instead of choosing VMFS or NFS, we build a data store for virtual volumes. From there, instead of choosing a LUN or an NFS export, we'll choose the storage container that the storage administrator has built for us. What you'll then see from the vSphere admin side is the same thing the vSphere admin has always seen. The data store and the virtual machine files inside. From the storage admin side, on the other hand, you'll get a view into the virtual volumes or the vVols that lie on the storage container. You're seeing here a screenshot from one of Dell's implementations, and the view that you have will be dependent on the implementation of virtual volumes done by your storage vendor. But the point here is that you can create a mental map between the quote-unquote file view that the vSphere admin gets and the actual vVols view that are seen on the array. So now that we've talked storage containers till we're blue in the face, let's move to the data plane where we have our protocol endpoints. Again, why the PE? Because of the challenges introduced with the dual-purpose nature of the LUN. We simply don't need as many access points as we need storage containers. So as we separate those jobs, the storage container provides the place that we store our virtual volumes, and the PE provides that access point. The PE provides that I/O channel between ESXi and the storage container. A few points then to mention about protocol endpoints. First, they are a construct of our virtual volumes enabled arrays. They're created by the storage administrator to enable access to the storage containers by one of the supported protocols. So the first thing the storage administrator will do when they get their shiny new virtual volumes array all racked up and powered on is that they're going to go into the management interface on the array and create at least one PE. And that PE will be set up for access as either iSCSI or NFS version 3 or Fiber Channel or FCOE. You're going to want to support, if you want to support multiple protocols, you'll set up multiple protocol endpoints. So remember that all that time you spent trying to decide which type of array to buy, which type of storage infrastructure to build, well, with our new abilities in virtual volumes, with our abilities to offload all those provisioning tasks directly to the arrays, we've completely leveled the playing field between all of the protocols. At this point, all you really need to be concerned with is whether or not there's a virtual volume sticker on the outside of the box. From there, just choose the protocol that matches the physical infrastructure that you already have in place. Choose Fiber Channel if you've got SAN switches, choose iSCSI or NFS if your infrastructure is built on Ethernet. If you have an existing relationship with a storage vendor that might favor one protocol over another, great, then go with that. Okay? Now, one more thing to discuss here, and that's how we handle multipathing. Now, we can also bring the concepts of zoning in here as well because multipathing and zoning policies previously applied to our LUNs. But it was the access point job of the LUN that we were dealing with. So your multipathing and zoning policies will then naturally apply to your protocol endpoints now instead. So as we continue our story of virtual volumes, it becomes clear that we've replaced the concept of the LUN with protocol endpoints and storage containers, all while removing all the restrictions that the LUNs placed in our environment. So when it comes to multipathing and zoning, we work in the exact same way that we always have, but now we apply those concepts to the PE instead of the LUN. With zoning, we can then determine which PEs are exposed to which hosts, and with multipathing, we can choose which algorithms the host is going to use as it accesses our protocol endpoints. So in the end, we've got three different constructs. The first two are created on the array. These are the protocol endpoints, which serve as the I/O path to direct ESXi to the storage itself, and the storage container, which serves as a logical grouping for our virtual volumes. Tying those two constructs together is the job of the data store. The data store says to ESXi, you want to access your storage container via the iSCSI PE, send it over here to data store X. You want to access that same storage container via NFS, send it over here to data store Y. Okay, so I've done all this work on the array. I've created the protocol endpoint, I've created the storage container. Now what? Now ESXi needs to become aware of it. And just like we do when we create a new LUN, we begin the discovery process so that we can begin interacting with this newly available storage. So there's a little button in the storage management section of your ESXi host in the web client. Hover your mouse over that little button and you'll see what we're talking about, that we execute a rescan of all of our storage adapters. And during that rescan, we'll not only discover VMFS volumes, but we'll also discover new protocol endpoints. And when we discover that PE, ESXi now knows that the underlying array is a vVol array. So that's what we do with iSCSI or Fiber Channel Protocol endpoints. NFS PEs are maintained as IP addresses and file paths as we build virtual data stores on the NFS PE. ESXi will then maintain a database of all those identified PEs that it discovers. When a storage container is built, part of the specification, along with its capacity, includes other capabilities: snapshots, replication, the number of IOPS it can deliver, and so on, right? Once this is done, the Vasa Provider, this is the channel that we create between the array and ESXi, the Vasa Provider discovers the storage container and reports on its capabilities back to vCenter. More on the Vasa Provider in a little bit, okay? So this is a bottoms-up process. That Vasa Provider reports the configuration back to the host. Now don't confuse this with the PE discovery procedure, which is top-down. In that case, the PEs are discovered by the host during a scan. Now, at this point, things are really starting to come together. When we create a virtual machine, based on the storage policy we've selected for that VM, the VM's objects will then be placed on that storage container. Excellent. Now that we understand many of the new concepts that we are introducing in virtual volumes, we have the foundation to talk about how all this stuff comes together. We need some sort of management construct that allows the array to tell ESXi all about itself and for ESXi to place some demands on that array. That management construct comes to us in the form of the Vasa Provider. Okay. The Vasa Provider comes to us via a URL published from the storage array. And as we point vCenter to this URL, and our hosts now have a control path from which to execute the Vasa API primitives. So Vasa is a set of APIs that ESXi exports to the array. And the Vasa Provider is that interface by which we communicate those APIs. For example, one of our Vasa primitives is to execute a snapshot. So as a vSphere administrator, we decide to take a snapshot. Or maybe there's some other tool that's automated, or the vSphere API drives a process that executes the command, right? The host then sends that snapshot to command via the Vasa Provider, instructing the array to take a snapshot. Okay? The array then executes that snapshot in whatever method the storage vendor has decided to implement, whatever method the storage vendor has decided to implement snapshots on that array. So ESXi and vCenter drive these API calls to the array through the Vasa Provider, and in return the array provides vCenter and ESXi with awareness of its capabilities. Beyond that, we do something really, really special. Through the Vasa Provider, we give the array information about the virtual volumes. This way, the virtual volumes, the files of the VM, actually become native objects on that array, allowing the array to manage individual virtual volumes in much the same way that they used to manage entire LUNs. This way, we say that we don't really need a file system, right? We can use these APIs instead to inform the array that the files of the VM can be created as individual objects on the array, and the array can now manage these individual objects. Want to clone a virtual disk? Excellent. The array can now clone a virtual disk. In many cases, you can use a single Vasa Provider to manage multiple arrays from the same vendor. This is super cool because it allows our storage vendors to unify the management interfaces of an entire storage system. And vCenter only needs to know one URL in order to participate. So today, if you have a farm of 10 or 20 arrays, you can simply point to one URL, add a single plugin to vCenter in the web client, and in one shot, you're able to manage all of your arrays. Now, it's highly likely that your storage vendor has had the Vasa 1.0 APIs implemented for many years. So to implement virtual volumes, your storage vendor will likely ask you to perform a simple firmware update to support the new Vasa 2.0 API set. Now, in many cases, it's really just that easy to implement virtual volumes. Upgrade your hosts in vCenter to vSphere 6 and implement a new piece of firmware on your arrays. Again, in order to support virtual volumes, your vendor also has to implement the Vasa 2.0 APIs and publish them through the Vasa Provider. Now, some vendors are including Vasa 2.0 in firmware that comes right out of the box, and others are simply adding Vasa 2.0 and support for virtual volumes for their existing installed customer base by a firmware upgrade. It's really up to your storage vendor as to how they're going to deliver virtual volumes, which arrays they decide to upgrade, and how they're going to deliver those upgrades to you. And each vendor seems to be doing things a little bit differently. Either way, it's going to be pretty easy. Okay. Now, just to recap here, the Vasa Provider is an essential element in our virtual volume story. No Vasa Provider, no virtual volumes. Okay. So we're bypassing any need for a file system here by using this special set of APIs to instruct our arrays to create the components of the VM, the virtual volumes themselves, and they are created directly on the array as native objects. Now, by having the array get into the business of building virtual volumes, it opens up a whole world of possibilities. Even though as vSphere administrators and the managers of virtual machines, we know which VMs have which virtual disks and which VMs need more capacity and higher performance out of their virtual disks, we have very little ability to guarantee that our VMs actually do get that performance and gets those features that they need. But by granting this same awareness to our storage arrays, we can place the responsibility of delivering those VM requirements and guaranteeing that those requirements are met directly onto the shoulders of the array itself. If we need to support multiple disk failures, we can instruct the array to provision multiple replicas. If we need for a virtual machine to be encrypted, we can now instruct the array to encrypt the virtual volume instead of having to provide some sort of front-end encryption. If we want to make sure that the virtual machine is replicated to a second array, we can instruct the array to replicate just those virtual volumes instead of having to replicate an entire LUN. How much more efficient have we now just become? Performance is shot through the roof. Instead of having to spend multiple hours or even days to replicate an entire large LUN, we can now simply replicate a virtual disk, sometimes in just minutes. So how do we accomplish this? How do we actually inform the storage array that our particular applications and the virtual machines that drive them need specific things from the array? How do we tell the array, for example, that this virtual machine runs a database, and in order to run that database properly, we need at least 2,000 IOPS from the array? Or this other application contains highly sensitive data, so we'd like for this data to be encrypted on the array. Well, this is done through our system called Storage Policy-Based Management. The first thing we need to know is this: what features, how much performance, and what capacity is the array capable of delivering? Gee, if only we had some mechanism by which to discover this. Oh yeah, we got that Vasa Provider for that. Excellent. So now I know what my array is capable of delivering. We know our storage capabilities. The next thing that we need to know are the requirements of a particular application. Now, most of the time, that's an easy one. The folks that are responsible for ensuring the performance of those applications should be pretty quick with that information. We're then going to take the capabilities of the array and match them to the requirements of a virtual machine by building what we call a virtual machine storage policy. It's done right from the homepage of vCenter. Find that little icon that reads Storage Policies. It's been there since vSphere 5.0. So by taking the capabilities of the array as published by the vendor provider, we can create a storage policy that represents the requirements of a particular type of application. We'll actually create multiple storage policies, one for VMs that don't require vast capabilities, another for VMs that require very high performance, and so on. Then we'll apply these policies to a particular virtual disk on a particular VM. Now, it's great to have that granularity down to the virtual disk, right? After all, if I have a database VM with a C drive for the system disk and the database itself on the D drive, I don't need 2,000 IOPS for the Windows directory, right? From here, all we have to do is click OK. Commands, API calls are then sent to the array, who is now responsible for provisioning those virtual volumes, those virtual disks, on its storage in such a way that it meets the minimum requirements of the policy. We can then check to be sure that the virtual machine is compliant with the storage policy anytime we like. All right. Now, the next thing that we're going to do is look at then how ESXi actually gains access to a virtual volume. From the perspective of the vSphere administrator, it's pretty easy. We create a virtual machine, assign a storage policy to that virtual machine, and choose an appropriately compliant virtual data store. Under the covers, a few things happen that trigger operations to provision virtual volumes on those storage containers. These operations, as executed by the hypervisor, are translated into Vasa calls and then offloaded to the array, who then builds virtual volumes on the storage container in such a way that the array is able to meet the requirements of the virtual machine policy. So we're going to get our nerd on a little bit here with a process called a bind request. And this is what allows an ESXi host to then access a particular virtual volume that's already been created. Now, we start with a binding operation. This is that Vasa call that establishes the I/O path between ESXi and a particular virtual volume. So any operation that we need to do on a virtual volume is then offloaded to the array through that bind request. If we need to initiate a clone, we need to do a snapshot, any type of operation that we execute against that virtual volume, we do it through a bind request. Now, when that bind request is received by the array, a couple of things happen. The first thing that happens is a unique identifier, the PEID, is returned. That ID is then bound to a specific virtual volume. At that point in time, there's a unique secondary ID that surfaced up from the PE that is assigned to sustain that communications channel for I/O. Now, from the perspective of ESXi, for SCSI-based protocols, that secondary ID represents a LUN. Again, ESXi knows about LUNs. It doesn't know about protocol endpoints for I/O communications, right? So why reinvent the wheel? We'll just talk LUN speak, right? That's what that secondary ID does for SCSI-based protocols. For NAS devices, the secondary ID is based on the file path. So in terms of virtual volumes sitting on a storage container, there's a many-to-many relationship with a PE. In other words, you can access a virtual volume from multiple protocol endpoints. Binding operations are not only used to establish that relationship between a PE and a virtual volume, they can also be used to unbind that virtual volume, or we can rebind that virtual volume if we want to move the binding from one PE to another. The example we show here is for load balancing. So that's the story of our virtual volumes and provisioning workflows. With the virtual volumes infrastructure in place then, there are a number of different operations that can make use of the Vasa APIs to offload different tasks to the array. In some cases, you might want to migrate a virtual machine from a VMFS data store to a virtual volumes data store. So how is this accomplished? In this case, we're dealing with two different APIs, VAAI, or the vSphere API for array integration, and Vasa. Now, the one thing to note here is that if you're migrating from a VMFS to a virtual volumes data store within the same array, we are always going to default to using the virtual volumes primitives if we possibly can. If we're moving from one array that does not support VAAI to a virtual volumes array-based array, or virtual volumes-based array, then we'll have to use the ESXi-based data mover to accomplish the migration. So that's just one migration scenario that you might encounter. In the case where we're moving from a VMFS array that does support VAAI, then we can use the VAAI primitives to accomplish the migration. And that offloads the work to the arrays and significantly reduces the load on the hosts. There are other operations as well that we can offload to the arrays. These include virtual machine provisioning, delete operations, full clones, linked clones in view, virtual machine snapshots, and cold storage migrations. Storage vMotion operations, that is live storage migrations, are not offloaded to the array. However, if a virtual machine happens to have snapshots, the migration of those snapshots can be offloaded to the array. Using the Vasa APIs on a virtual volumes array, we can offload a cloning task directly to the array. The array at that point will use a cloning mechanism built by the vendor to execute the clone of virtual volumes. If we're cloning from a VMFS data store to a vVols data store, we can then use the VAI primitives instead to execute that clone. Now, when executing a clone or other operation from a storage container to a storage container, we'll always first attempt to use the vVols primitives. If for some reason that fails, we'll go ahead and use VAI to offload the operation to the array. Snapshots are now offloaded to the array as well, and they're one of the many data services that we can execute via our Vasa API calls. When executing snapshots, there's a couple of things that happen. Some common capabilities that exist within our platform that you already use. You might be used to executing snapshots from the vSphere client, and prior to virtual volumes, this was the only type of snapshot that we supported from ESXi or vCenter. This is the traditional vSphere snapshot that we're all familiar with. But we also have the concept of snapshotting at the array. So we can use a managed snapshot. That's a snapshot managed by vSphere. Or we can use an unmanaged snapshot. Those are snapshots taken by the array. Either way, we're now creating snapshots as a copy on write of a virtual volume. Based on the type you use, we'll either have the ability with vSphere-based snapshots to support up to 32 snapshots on any single virtual volume, okay? Or using unmanaged array-based snapshots, we're going to default to any limitations that the array vendor might have. VMware actually anticipates that early generations of virtual volume storage systems will support on the order of tens of thousands of snapshots. Okay? At that point, it's based on the array's capabilities. So that's my story, and I'm sticking to it. By this point, I hope that we all understand the value proposition here. Why make the move to virtual volumes? Because virtual volumes simplifies storage operations by automating manual tasks and eliminating operational dependencies from between the vSphere admin and the storage admin. Provisioning becomes faster, change management becomes simpler because of policy-driven automation. Virtual volumes simplifies the delivery of storage service levels to applications by providing administrators with far finer control of storage resources and data services at the virtual machine level, and these requirements can be dynamically adjusted in real time. Virtual volumes improves resource utilization by enabling more flexible consumption of storage resources when needed and with greater granularity. The precise consumption of storage resources eliminates over-provisioning and reduces management overhead. This is where we get to brag a bit and offer lots of kudos to our fine storage partners. They've worked really closely for VMware for several years on this project, and we're finally getting to see the fruits of everyone's labor. With virtual volumes, we've created an industry-wide initiative that allows customers to leverage the unique capabilities of their current storage investments and transition without disruption to a simpler and more efficient operational model optimized for virtual environments that works across all storage types. Currently, there are 29 partners and growing working with VMware on virtual volumes. Many currently have shipping product, and many more are right on the cusp of release. We are very proud to say that each of these partners are bringing something unique to the table, so as consumers of these storage systems, we've really got a lot to choose from. If you want to know more about virtual volumes, there are lots of resources out there. First of all, you can go straight to vmware.com/go/try now. and have a look at lots of different VMware products with a hosted evaluation. It's really, really a neat environment that you can work with. VMware blogs are available, blogs.vmware.com, that really speak to this topic and lots of other topics, and they're very well written. The communities are also an excellent place to go to find out more information, to ask questions of VMware employees and other VMware users. I use this every day. And of course, there's the knowledge base articles. I always say, when all else fails, read the manual, right? That's where the knowledge base articles come into play as well. Another really excellent resource that you have if you're interested in learning more about VMware products or you're studying for certification is something called the VMware Learning Zone. The VMware Learning Zone gives you all kinds of really great videos that have been produced by myself and my colleagues at VMware to teach you about all kinds of different topics. Okay, there's a special right now going on, $500. That's half price for a limited time. Gives you a year of access to the VMware Learning Zone. Now, my colleague Brett Guarino will be joining us on September 16th for the next webinar on vCloud Air. Some really, really cool stuff going on in the cloud with VMware, and if you want to know all about it, please join us on September 16th. Thank you so much for hanging out and listening, everybody. We're obviously here to answer your questions, so please throw them up in the chat window there, and we'd be happy to answer those questions that you've got. Thanks again for joining us. Take care.